So a little bit of history. So how did all of that came together? So we pretty much started that autonomous racing project late in 2017 at Technical University of Munich with a couple of PhD students. At that time, it was 5 people. We scaled it up to 7 and were able to participate at the Berlin Formula E race with the DevBot 1.0. And we made it to several high-speed trials, and we were able to do all of that doing an online mapping of the track geometry, planning of an optimal racing line, and then achieving speeds of around 150 kph. So even though that was a pretty nice achievement, we were aiming to push the limits a lot further. So we redeveloped a couple of algorithms and gone to various circuits all around Europe in 2019. So we made it happen to do the first passing zone-based 2-vehicle overtake in April 2019, together with the company RoboRace and Arrival. So those cars were going, actually with 2 cars on a track, and they were going side by side as soon as they entered a certain passing zone, and then they were allowed to safely overtake each other. That was done at speeds at around 160 to 180 kph, so even a little bit faster than what we've been doing previously in Berlin. But as soon as you go faster, also the first things can go wrong. And so we had the first real software-induced high-speed racing incident in May 2019. I don't know, but that's probably the first one I was aware of, which was happening as a major at a major racetrack while we were pushing the limits of the car. So, and this was a failure which was induced by an actual algorithmic error, and it wasn't a failure induced by pushing the car too much over the limit. So, and the pretty interesting thing about that was this was a software version which was well proven, and there were just a couple of slight parameter changes which induced an error mode which wasn't tested before. So, I think what we learned back at that day is that it's actually pretty hard to develop autonomous racing algorithms. And I think that's already one of the learnings you can take from autonomous racing, that if you push it to the limit, things will go wrong, and you actually have to take that into account. And especially if you're trying to build a product which is going to be out there on the streets. So fast forward 2 years. So we decided to join the India Autonomous Challenge. So after a couple of simulation races, we made it to real world testing with our friends from all over the world. So what we see here in the picture is the Euro racing car and our car going head to head on Lucas Oil Raceway. Obviously that was started pretty slowly. So yeah, these cars were driving at that time 50, 60, 70 kph, but they were going head to head without any specific route. So they just perceived each other, predicted what's going on, and then overtook as soon as they felt it was safe to do so. And that was a pretty major step for us, especially as we have been removing all of the inter-vehicle communication, and the car has been actually doing all of the functionality on board. So as Madhu already mentioned, going to October 2021, we managed to win the first India Autonomous Challenge with a car from TUM. It was a very, very close finish with the 2 other Italian teams. So what we did there is successful static obstacle avoidance and matching a 2-lap average of 218 kph. That was essentially the fastest 2-lap average, which made us the winner of the first competition. Finally, the competition was extended to go to Las Vegas and made the real passing competition happen. So based on a pretty interesting competition format where the cars were stepping up the speeds on a per round basis and had to overtake each other from first the first car was limited at a certain speed, and then the second car was overtaking, and then it was doing that vice versa. So we actually placed second here in a very close final together with Polymove, and we reached actually the maximum of the cars. And I think that's a pretty remarkable achievement, that this competition was actually ended at a situation where the cars have been maxed out up to their top speed. And that shows that the progress in autonomous racing has been tremendous over the last 4 to 5 years. But there's also, it shows that there's a lot more to do, and that's going to be the topic of this talk. So just to motivate that a little bit of what we're doing here at driveblocks, it's so we're taking all of those learnings and actually building a modular and scalable solution for commercial vehicle driving. So it's actually the idea is to not build like 5 or 10 building blocks, but actually build 200, 300, 400 very small building blocks and be able to recombine that in various ways to solve a lot of different problems. So these problems could be in mining, they could be in container terminals, but they will eventually be also on the road. I think what's unique about what we do that is a lot of that is based on open architectures and open source technologies. And obviously, several of the design choices we are making are inspired by our learnings from the Racetrack, which we're now taking to the actual commercial vehicle production. So that's it about the, let's say, slow commercial vehicles. And I'm going to dive into much more detail and what we believe can be learned from racing autonomous cars. So the first thing, and I think that's probably the most important one, is going fast means going safe. So what we have seen is that as soon as you hit certain top speeds, a lot of things happen very, very quickly. So you just have to think about that the top speeds of those Indy autonomous challenge cars, they move 75 centimeters within 10 milliseconds. That's really a lot of movement and a lot of motion, and it becomes apparent that it's very hard to actually control those cars precisely, and that there's a lot to learn from that precision. Because if you're able to control the cars at those speeds very precisely, that's going to transfer in reduced braking distances, in reduced reaction times, and therefore safer autonomous vehicle technology for production grade vehicles. So I think this is a pretty apparent overlap between autonomous racing and the actual like production vehicle development. It's not about that a production vehicle has to go the same speed as a race car, but it's about all the techniques you learn in programming, about the techniques you learn in your algorithmic development to actually enable to reduce the latency of your software stack and therefore reduce braking distance and reduce the reaction times which a car has in any kind of difficult situations. Here we go. So adding onto the points Marco made earlier, we also found that it's one of the challenges is if you go really fast, that your reaction times and your real-time behavior of the code has to be pretty much on spot. So when you want to leverage those computers which are in those autonomous vehicles, you have a ton of CPU cores, which are sometimes pretty powerful, sometimes they're less powerful, and you have a lot more cores. But all in all, it always comes down that you have a multi-core system where you want to achieve minimum latency. And you have a compute graph, which can be pretty complex. So we see an example here on top where you can see like 3 sensor inputs, which are processed through multiple steps and then fused with 2 different algorithms. And this kind of processing can be pretty challenging to schedule. And it's really important to think about those implications when you design your system, when you develop the software. And it's actually also a challenge to implement all of that, such as capable of running in a real-time manner. And we've been doing that mainly in conjunction with the ROS2 code base. We have been working closely with the people at Apex and the ROS2 real-time working group there to actually understand how to build a ROS2 system which can handle all of those requirements and actually be as close to real-time as possible. So what we found is that it's pretty important to actually adhere to standard real-time programming principles. So you shouldn't do any file operations, you shouldn't do any console operations. And even though that sounds pretty obvious to the folks from the real-time community, we have found that this is something which wasn't really, let's say, present in the autonomous racing community. And that is actually a topic where we believe there's much more to do, especially if we're trying to push the limits of the technology even further. Another thing we had to do is that there was a lot of advanced configuration required on the thread priorities, CPU affinity, and resource constraints to actually prevent all of those different software functionalities to interfere with each other and really ensure that they do what they actually should do. And all of this is like, it's pretty hard to dive into it, especially as it's hard to debug these kind of systems. So we believe that autonomous racing is actually a great platform to understand how these kind of challenges can be solved. And this will also, in the end, translate to safer and more autonomous vehicles on the road. Another point which I want to highlight is that today, most of the autonomous racing vehicles are equipped with like pretty expensive server-like CPUs, GPUs, which are built for gaming. There are switches which you find in server racks. And we have found that it's actually going to be a challenge to merge them towards more embedded to more embedded CPUs and ECUs. But I think this is something where the autonomous racing community can actually really showcase what the state-of-the-art compute platforms are capable of doing. But at the same time, it should also be a reminder to the community that it's really worth to invest in bringing those algorithms onto those platforms, understanding how the open source tools like ROS2 and these kind of things can be brought onto those platforms. And it's really an important problem where the industry is struggling to solve at the moment. Come on. So another real world example, which is pretty interesting, I want to walk you through, is what happened at the end of the final with Team Polymove. So what we see here on top is those two cars driving around 250, 260 kph. And that's pretty fast. And at the same time, we found that, so what we have been seeing here is that the back car, which is the TUM car, actually had some misdetections within the radar object detection. And that led to the car initiating an emergency evasion maneuver. So the car on the third picture is actually starting to turn left. You can see that on the fourth picture as well. And this wrong detection in the radar actually made the trajectory planner think that there is an object really close by and that it has to do a really hard emergency evasion maneuver. And this emergency evasion maneuver wasn't able to be executed in a valid way because it was just too much for what the car could handle from a vehicle dynamics perspective. And again, this translates to what's actually one of the challenges which the industry faces today. Because like a single misdetection can cause an autonomous car to stop or to do a sudden emergency brake, which is really, let's say, impacting the ride quality or the operational quality of those vehicles. So increasing the reliability of the sensors, of the detection algorithms, and the downstream processing pipeline is something which is where the industry can test their approaches within the autonomous vehicle domain without actually doing any harm to the outside. There's no risk involved because if you're at the racetrack, really, nothing bad can happen despite a car crashing into a wall. Another interesting challenge which we found during our development is what we call the chicken and egg problem of purely self-driving vehicles. So what's pretty prominent in the research community is the deployment of advanced deep learning methods. So let it be for object detection, let it be for prediction models. There are various applications, but all of those models actually need a lot of training data. And the issue here is really that if you have a purely self-driving vehicle, which can't be driven by a human test driver, so how do you actually acquire the training data you need to train your models? So that became really apparent during the first testing days, where you're actually in the situation that you have to do with the car what it should do, and you find out, okay, I can't do that prior to training my models, but I can't train my models prior to my car driving on the track. And this is something where we believe is actually going to be challenging as well for the industry as soon as we move towards more, let's say, fully self-driving vehicles and vehicle designs which are optimized to not have a safety driver on board anymore, because those vehicles will actually will actually face the same difficulties as we have been facing during our development. How we overcome this is by basically a mix of different techniques. So first of all, we use synthetic data generation, But we also combined this with the application of classical computer vision algorithms and eventually a gradual increase of the complexity. So start driving slowly, collect the data you need, retrain the models, and then the models improve and you can actually go faster and be like reduce the safety distances and these kind of things. But that's a real challenge you face if you have to deploy your models in the real world and you're actually going to run them on a real car. One of the probably most important things to which we found during the Indy Autonomous Challenge was a really sophisticated testing and simulation workflow. So we had a 3-stage process there, and that's so first of all, we had really test cases on like an algorithmic or module level. So each of those algorithms could be tested independently, either with log data replayed or with like really stripped down simulation models, which were only handling that specific problem. If these algorithms pass those tests, you go to like a full stack simulation environment. We invested a lot of time to really like model what's going on there in detail, not only the vehicle dynamics, but we were also able to simulate various different vehicles. And that was a big learning for us, that it's actually really different if you have multiple autonomous vehicles on the track instead of just having 1 or 2, because all of them can start to interfere. They do like pretty crazy things if the algorithms are not well tuned. And there's a whole new dimension. And we believe that it's going to be a pretty important topic for the industry to actually simulate in complex multi-agent environments prior to going to real world testing. Yeah, so that was always the last step, always the most risky one, but always, but also the one where you could learn the most. So finally, I think I want to highlight 2 more points in why autonomous racing is just a great driver for the industry. So it has been, so from my perspective, the Indy Autonomous Challenge and RoboRace have been great catalysts for the open source ecosystem. So a lot of teams used code, for example, from the AutoWare Foundation. A lot of teams have been building on ROS. So there has been a lot of work to actually not only use those things, but a lot of the stuff has been contributed back to those projects, and there was a lot which could be learned. So we believe that autonomous racing is just a great showcase to what's going on and to really demonstrate that that open source technology is really capable at the state of the art. And finally, the last point is autonomous racing is just a great test bed for the next generation of software developers and people working on autonomous driving technology. And it's really, it's not only fun, but there's really a lot of skills which are learned in taking part in those challenges. And I think what I want to say here is that I want to encourage everyone to actually work with those teams, let it be in the F1 10th, let it be in the Formula Student or at the Indy Autonomous Challenge next year. Even though it's going to be a ton of work and really a lot of time which we are going to spend, I think it's worthwhile doing, and there's a ton of things which you can learn from doing so. All right, so that's it from my side. Thank you very much, and thank you for having me, Madhur.
All right, thanks, Alex. Great.